Good morning. How was your night? Okay. So let's get started. So yesterday I left you with a problem. Who was able to clear the puzzle? Who was able to clear the puzzle? Okay, yesterday was greater than 0. And today is less than 0. It can be less than 0. It can be greater than 0. And yesterday we said that this on this is what? Is one. Are you sure? It's equal to which is equal to which is equal to which is equal to k squared on c squared, or k on c squared, into 1 over r minus 1 over r e. Is that not? That's what we had yesterday. This is what we had yesterday. So we are saying that if delta V or delta nu is, okay, you are comfortable with greater than 0. Okay, if it is greater than 0, then it implies that 1 over RR is greater than 1 over RE. Is that not? Is that not? To give you a positive number. This is greater than 0. So we want a number greater than 0. So we want a number greater than 0, then this must be greater than this. Okay? And in that case, this will be less than this. Is that not so? In that case, the point of reception will be closer to the massive body than the point of emission. So the signal is emitted from a point further away. Okay, so we have something like this. So the point of emission is further away from the mass than the point of reception. Okay? It's further away than the point of reception. And this is greater than 0. Remember, this is frequency. Frequency at emission, which is always a positive number. So, whether it's greater than 0 or less than 0 is from this difference. Is that not so? It's from this difference. It's this difference that makes it either greater than 0 or less than 0. So this difference, if this difference is greater than 0, then what we are saying is that what? That there is an increase in frequency. Is that not? There's an increase in frequency from emission to reception. And is it a blue shift or a red shift? That is where we added yesterday. Is it a blue shift or a red shift? I want to claim that it is a blue shift. I want to claim that it's a blue shift. And in the other case, it's a red shift. I expected you to have read about this yesterday. So what do you use your evenings for? I expected you to have read about this. I expected you to have read about this. But what is a blue shift? What is a red shift? Okay. Yes. There's always a yes. Okay. So go and read more on that. Go and read more on that. Okay. So we also looked at length contraction and time dilation. So today we are going to move 2 steps further. Okay, we'll look at motion of particles of non-zero rest mass. Okay, then we'll look at gravitational deflection of light. Okay, so there are 2 types of particles there. Particles of non-zero rest mass. Okay, and then photons or light, which we consider to have a negligible rest mass, a rest mass which is almost 0. So we will have that. Okay, we have that, and a particle in this case can be as large as a star. Okay, our notion of particle here is different from the notion of particle in particle physics. Okay, so a particle can be any mass. Anything that has mass is a particle. Okay, so we'll go into that. And remember, we are working in the Schwarzschild field. We are using the Schwarzschild field as an example for us to appreciate all the astrophysical phenomena. Okay? So we now want to look at motion of particles of non-zero rest mass. Okay? And we agreed the other day that our equation of motion for particles of non-zero rest mass is of the form d squared x of mu g2 squared, okay, plus, which symbol is this? Capital gamma. Okay. Dx mu d2 dx lambda d2 equal to 0. That's our relativistic equation of motion for particles of non-zero rest mass. Remember, our metric tensor is of the form 1 plus, let me use another notation. So what is our F? What is our F? Minus okay. Because we need to find this. We need to find this in order to use this equation. And we can only find this using this. Okay? We can only find this using this. We can only find this using this. So the first thing we need to do is to find this. We need to first of all find the covariant metric tensor. Okay? And I said the other day that this by that's what we said the other day. Okay? So, and remember the indices run from 0 to 3. The indices run from 0 to 3. Okay? So, if I decide, remember this is the same as this. I can set this to be 0. Okay, if I set my this to be 0, then I'm going to have G0 that, G0 that should be equal to that sigma lambda. Okay, and remember this can run from 0 to 3. This can also run from 0 to 3. But I now need to use my intuition and come back to this. What is the only covariant metric tensor that has 0? here is this one. Okay, so I don't need to investigate the other ones. Because if I put 1 here, it will give me 0. If I put 2 here, it will give me 0. If I put 3 here, it will give me 0. So I will not waste my time doing that. I know that the only thing that will survive is when this is 0. Okay? And I also know that if this other one, okay, if this one takes a different number from this other one, I'll have 0 at the right hand side. And it will also give me 0. Are you getting the point? So I need this and this to be equal to give me a 1 here. Am I making sense? Okay. So the only surviving entity will be G00, G00 equal to sigma 00, which is 1. So my G00 will just be 1 over G00. Okay? So it will just be, so my G00 is 1 plus F to the power minus 1. And the same applies for the others. Okay? The same applies for the others. Actually, this metric tensor is simple because it's a diagonal metric tensor. So for a diagonal metric tensor, to get the upper ones, if you are familiar with the process, it's just the inverse of the, to get the contravariant is just the inverse of the covariant. Okay, but you get to situations where you cannot use this. There are more complex situations where you cannot use this. Okay? There are more complex situations where you cannot use this. This looks simple, but it will be more cumbersome using it. Okay? In that situation, we use another formula. We use G mu nu is equal to the cofactor of G mu nu over the determinant of G mu nu. So we use that one. When we have a more complex metric tensor that has off-diagonal elements. When you are using this one, it will be more complicated for you. But you can still use it. But you will need to do a lot of algebra. But with this, it will be very easy for you to get it. Very, very easy for you to get it. Okay? If we look at mathematical methods by Afkin. Okay, mathematical methods by Afkin. This is well spelled out there. Okay, you can use that one. Okay? So what we are concluding is that our G11 is minus 1 plus F. Our G22 is minus 1 over R squared. Now G33 is minus R squared sine squared theta to the power minus 1. So far, so good. Any question? Any question? One thing with handling tensors is that you need to be very careful. Okay? If you look at the steps I outlined the other day, how you move across, you discover that if you make a mistake in step 1, that mistake will follow you to the last step. Okay? That mistake will follow you. And at the end of the day, you might get something that will be physically difficult for you to interpret. So you need a cool head. Okay? You need a cool head to do it so that you don't end up mixing things up. Okay? There are times you will do this more than 10 times. Okay? More than 10 times. I still have a very big file of this when I was doing my PhD. A very big file. I will do it and repeating, doing it. When I take it to Prof will say it's wrong. I'll go back and start from step 1. Okay, and maybe at one point it's just a minus. Just a minus that you are supposed to put and you didn't put. And then it rubbishes all your effort for the whole night. So you need to start afresh. Okay? So, we've gotten this, we have this. So we are now prepared to get this. Remember, I said the other day there are 64 in number. Okay, there are 64 in number. So I'll get just 1 or 2, and then I'll state the other ones. Okay? I'll get just 1 or 2, I'll state the other ones. Then we'll now try to solve this equation. Because we can't solve this equation without this. So I'll try to get 1 or 2. Then from there, we will now solve the equation. I'm taking my time on this because we are going to do it. Okay? We are going to do it. We are going to do the it. Because immediately after this, we'll start looking at some point to okay. Okay, so you see, after this, we'll start looking at some okay. Okay, so as I said on day 1, this is the problem we'll try to address in this center during our stay here. Okay, we are going to look at the astrophysical study of gravitational fields around spherically symmetric plasma stars. Okay, so we are going to solve that problem. And these are some of the tools we are going to use. Okay, so we'll divide this problem into sub-themes. And then you'll be divided into groups to solve it. Okay, so that's what we are going to do. So that's why I'm taking my time on this, so that you get the intricacies of what we are supposed to do. Okay, so let's try to get our lambdas. Let's try to get our lambdas. Lambda is defined in terms of our metric tensors as a half G sigma nu into G mu nu comma lambda plus G nu lambda comma mu minus G mu lambda comma nu. Okay, so that's our lambda. So this is how you do it. You set this. Remember I said earlier that this runs from 0 to 3. Each of them runs from 0 to 3. So first of all, set this, let's say to 0. Okay? If I set this to 0, I will permute these two. So these two will give me 16 with 0 up here. Do you get the point? Remember, there are 64 in number. There are 64 in number. So once I set this to 0, then I can permute these two. Okay? I can permute these two. Remember, I have 0, 1, 2, 3. 0, 1, 2, 3. So I will have 0, 0, 0, 1, 0, 2, 0, 3, and so on. 16 of them. When this is 0. Okay? So I'll have 16 of them. When I finish with those 16, I'll come back and set this to 1. And still evaluate 16. Set it to 2. Evaluate 16. Set it to 3. Evaluate 16. So I'll end up with those 64. Okay? So I'll now have 64 of them. But again, we have differentials here. These are partial differentials with respect to this. Actually, this one means G mu nu comma lambda is just partial G mu nu by partial lambda. That's what this means. So you differentiate this with respect to this. Okay? So when we come to our metric tensor, we'll be able to see where these differentials will survive. Okay? Remember, our CT is 0. Our R is 1. Our theta is 2. Our phi is 3. Okay? So if I have comma 1, I'm differentiating with respect to R. If I have comma 2, I'm differentiating with respect to theta. If I have comma 3, I'm differentiating with respect to phi. Okay? So if I'm looking at my metric tensor, I will know that this one depends only on what? This one depends only on which is 1. So any other differential of this 1 with respect to 0, 2, 3 will be 0. Only when you are differentiating with respect to 1 that it will survive. Okay? Same with this. Do you get the point? But this other one depends on same one. Depends on R. So any other differential that is not with respect to R will be 0. Then when you come to this other one, it depends on 1 and 2. This one depends on 1 and 2. So only differentials with respect to 1 and 2 are going to survive. All the other ones will be 0. So once you have this background knowledge, it will be very easy for you to simplify this problem. Okay? So let's start with the first one and see how it goes. Okay. So if I set this to be 0, then my first permutation of this and this is 0, 0. Is that not? So I can have okay. So from there, I have a half G. Remember, this is 0. This other one too is okay. This one is also 0. This one is also 0. Is this equation correct? Okay. I think it should be lambda here. Because if it is mu, it's going to cancel this other mu. But there's mu on the left-hand side. So the new parameter we're introducing is lambda. It's lambda. So this should be lambda. We'll check that later. This should be lambda. So that it will survive here. Okay. And then you now have G 0, 0, comma lambda plus G 0 lambda comma 0 minus G 0 lambda comma 0. Are we together? Are we together? Are we together? Okay. So remember, I can set this to 0, to 1, to 2, to 3. Okay. But I know that if I set this to be 0, I have something with it. If I set it to be 1, I have G01, and there's nothing here like G01. Okay, G01 is 0. These are the only non-zero components we have. So if I set this to be 1, this will be 0. So the only thing that is going to survive will be when this is 0. So I will have a half G00 into G00, comma 0 plus G00, comma 0 minus G00, comma 0. And then our G00, does it depend on 0? Does it depend on 0? It doesn't. It doesn't depend on 0. It depends on R. It doesn't depend on T. It's not a function of T. Since it's not a function of T, this will all be 0. So this is 0. Okay. Let me look for one that is not 0. Let me look for one that is not 0. Are we together? Are we together? Can we look for a non-zero gamma? Okay, let's take a non-zero gamma. Let's take a non-zero gamma. And let's take 0, 1, 0, 0, 1. 0, 0, 1. Okay. So again, we are going to have a half G 0 lambda into G, this one is 0, 1, comma lambda plus G this is 1 lambda comma 0 comma 0 minus G, our mu is 1 lambda comma 0. Will this one survive? This one is supposed to survive. This one is supposed to survive. When lambda is 0, all of it is 0. Is that not? When lambda is 0, all of it is 0. I'm scared I still have a problem with this formula. Something is wrong with it. Let's use the initial one I put and see how it goes. Okay, so in this case, we have G, so our sigma is 0, our this is 1. I'm not too comfortable with this formula. Into G, we have mu is 0, 1, comma lambda, okay, plus G, our mu is 1. Our lambda is there, comma mu, which is 0. Okay, minus G we have 0, lambda, comma, 1. Yes. Okay. This was. Okay, this one's. Okay. So we have that.
That is called new. That is N in Greek. The one that goes from down to this, which doesn't have, is called new.
This one.
And that's new. The other one is new.
Okay. So if we are going by this, then this will not survive. Okay? So that's why I will go back and check this formula. I'm not too sure about it. It's correct? Okay. But if you look at what we have on the board there, it will not survive. It won't survive. But from Schwarzschild's solution, we are given the only surviving gammas as gamma 0, 0, 1. It's among the surviving gammas. But if you look at this, as you have G01 here, automatically everything is 0. Automatically everything is 0. Which is not supposed to be like that. So I will check it. I will check it again. Okay? So the surviving gammas are F prime over 2 into 1 plus F. That's the first surviving one. So we'll revisit this again later. Okay? We'll revisit that later. And then another surviving gamma is gamma 1, 0, 0, which is 1 over 2 c squared f1 into 1 plus f. Then you have 1, 2, 2, which is minus r into 1 plus f. Then you have 1, 1, 1, which is minus a half f prime into 1 plus f to the power minus 1. And then you have the 2's. 2, 3, 3, which is minus sine theta. And then you have, there's also 1, 3, 3. 1, 3, 3, which is minus r into 1 plus f sine theta. Okay. And then you have 3, 3, 3, minus sine theta. And 2, 1, 2, 1 over r. You have that. And then 3, 2, 3, which is cot theta. So how many of them are there? 9. Okay? Yeah, 9. I'm using F prime here. F prime is just GF GR. Or F prime is GF by GR. Okay. Any questions so far? Any questions so far? So with our gammas, we can now get our equations of motion. Okay? We can now get our equations of motion. We can now get our equations of motion. So our equation of motion for test particles. Okay. So how many equations of motion do we expect? How many equations of motion do we expect? How many?
9.
Okay, he said 9. You think? Okay, he said 4. You said 3. Okay, okay. Yeah, the opinion of 9. Okay, why 9? Okay, we have 9 different gammas, so we have 9 equations of motion. Do we agree? Okay, Oga says no. Why? Uh-huh. Okay, he said 4. He said 4 equations of motion, and that is correct. Look at this. This is a second order differential equation. Okay? So the number of equations will be determined by this. The number of equations will be determined by this mu. And remember, mu takes values from 0 to 3. Okay? Mu takes values from 0 to 3. So we'll end up with 4 equations. The first equation will be when mu is 0. The second equation will be when mu is 1. The third one will be when mu is 2, and so on. Okay? So for us to get our first equation is to set mu equal to 0. So if we set mu equal to 0, we are going to have d squared x 0, the tau squared plus that 0, okay, the x of that, the x of that should be equal to 0. Okay? Are we together? I want us to be together. I don't want to leave anybody behind. I want us to be together. But there are some people, no matter what you do, they always want to be behind. They like to lead from behind. You know, there are two types of leadership. You can either lead from behind or lead from the front. Okay? And actually, if you look at it, leadership from behind, it is even more better than leadership from the front. Okay? When you are leading from behind, you empower your subjects. You trust their abilities. You ask them to explore their potentials. And then you only sit from behind and advise. Okay, when you lead from before in front, you go ahead and they follow you. Okay, and if you go into the animal kingdom, there are animals that lead from behind, and there are animals that lead from the front. Okay, so we have this. So we need to revisit our gammas. So what will happen now is we have gamma with 0 up here. So all the gammas with 0 as the superscript will feed in. Do you get the point? So we'll come here. How many gammas do we have with 0? We have only this one. So is that one will fit in here? Okay? It's going to fit in there. It's going to fit in there. So we are now going to have so this one is 0, 1. Okay. So at this point, we can decide to substitute our gamma and the expressions for that. So we are going to have this squared. What is our x0? Okay, over the tau squared plus this one is f prime over 2 into 1 plus f. This one is d of ct, the 2, and then this one is d of R into okay, so we are going to have that. I still need these gammas. Still need the gammas. Okay, so that will be, what is my F prime? Remember, my F is what? Minus 2gm over c squared r. So what is gf? Gr. What would that be? What is it going to be? What will it be? Let me use K here. What will it be? Two K over C squared R squared. Okay, because the minus from the differential will cancel this. So we'll have that. Okay, so we can write this as C T dot dot. Okay, T dot dot plus our F prime, which is 2K over C squared R divided by 2 into 1 minus 2K, it's a squared here, 2K over C squared R. Okay, so we have C T dot by R dot should be equal to 0. I'm going to have that. Which is going to reduce to T dot dot plus K over C squared R squared, okay, into one minus 2K over C squared R. Okay, you have T dot R dot equal to 0. I'm going to reduce to that. So that's the time equation of motion.
Why if I use my time component without the
What if you use your time component without the C? That is not how our metric metric tensor is defined. It has to go with C. Because if you look at your line element is this S squared equal to C squared, the T squared. Okay, so actually you have minus the r squared minus r squared the theta squared minus r squared sine squared theta the phi squared. Okay, so this always goes with that. With that. Okay, this is c dt. If it's not c dt, it will make the dimensions of this equation wrong. Okay, this equation will not have it will not be a distance. So the c is there to make this a distance. You cannot just use dt. If you use dt, you will be wrong. Okay. Any other question? Any other question? This is a differential equation, which we can solve for t. That's the equation of motion. And when we solve for t, we'll end up with that gravitational time dilation. Okay? So it describes the way time changes in a gravitational field. When you solve this, you will end up with that expression we had for gravitational time dilation. Okay? Okay. I can write that equation as t dot dot over t dot is equal to or plus k r dot over c squared r squared into 1 minus 2k over c squared r. You can write this equation like this. That's just dividing all through by t dot. Okay? And I want to claim that this equation is the same as d the tau of ln t dot, okay, plus d the tau of ln 1 minus 2k over c squared r, all of that divided by 2 equal to 0. Can you see it? If you differentiate this with respect to proper time, it gives you back this. When you differentiate, you have t dot dot 1 over t dot. Okay? T dot dot 1 over t dot. So it will be t dot dot over t. Okay? And once you differentiate this other one, you will get this, which is outside here. Okay? With the r dot, and then you now have 1 over that. So it gives us that. And if you look at this, you can also conclude that ln t dot plus half ln 1 minus 2k over c squared r is equal to a certain constant, say a. Okay? You are differentiating something that's giving you 0. So automatically that thing is a constant. Then using our basic knowledge of logarithms, we can combine these two. Okay? We can combine these two as ln t dot into 1 minus 2k over c squared r to the power a half should be equal to a. Okay? Then you can remove the ln. Okay? So this will become e to the power a, which is another a. Okay? We got e to the power a, which is another constant, which we can decide to call it b, or we still call it a. So you end up with t dot 1 minus 2k over c squared r to the power a half equal to a. Okay? But remember, t turns to 2, okay, at infinity. Remember yesterday, I mentioned that proper time is the time that is measured far off from the gravitational field. Okay? So if t is turning to the proper time, then we are approaching that. And if t is turning to that, then t dot will turn to 1. Okay? VR is turning to that. So as r turns to infinity, t tends to 2. So what will happen is that if r is turning to infinity, all of this, where are we? If r is turning to infinity, okay, then our a will be 1. Our a is going to be 1. Because this over this will be 1. So at the end of the day, we come back to that expression we got earlier. That t dot into 1 minus 2k over c squared r is equal to 1. This is the expression we had earlier. So that's the expression we had earlier. What we had earlier was the t equal to 1 minus 2k over c squared r to the power minus 1 d2. That's what we had earlier. So we'll come back to that. Any questions so far? So that's just one of the equations. Okay, we can do the same for the second. We can do the same for the third. We can do the same for the fourth. Okay? We can do the same for the second, the third, and the fourth. Okay. So we don't need to go into all of them. Okay. Maybe we'll take the third one. We'll take the third one. And then from there we can look at something else. For the third one, only these two are required. We have 3, 3. Okay. Any question? So far, so good. So we are setting our mu as 3. Then we'll have 3 here and 3 here. Okay? So in that case, we are going to have d squared x cubed over the 2 squared plus, let me start with this one, 3, 2, 3 of the x 2, the 2, the x 3, the 2, plus 3, 3, 3 of the x3, the 2 squared equal to 0. I'm going to have that. So this would take me to, what is our x3? Phi. Okay. So it takes us to phi dot dot plus, this one is cot theta. This is r dot. This is phi dot plus, the other one is minus sine. Okay, minus sine, minus sine theta into phi dot squared equal to 0. Okay. We have that. Yes.
So the gammas now are get together. The gammas.
Yes.
Or thinking we do that of three this simple.
That of.
Like solve for 3, 2, 3. Gamma 3, 2, 3.
Mm-hmm. Oh, look at what happens. Once you put this 3 here, this 3 takes care of any combinations down this way. Can you see that? So this 3 will take care of all the combinations down here. So if there are even 10 components having 3 here, all of them have to be included in this equation. Because we'll end up just with 4 equations. We have just 4 equations. Okay. Okay. This one is theta. Is this theta or R? I wrote it and nobody said anything. This is theta. Theta. Okay. Let's have a short break. Then we continue. Okay, how we left from here to this. It's similar to the question he asked earlier. He said he expected this 3 to have its own equation differently and this one to have its own equation differently. Okay? But we have just 4 equations of motion. So once this 3 is here, then this 3 takes care of all the combinations of nu and lambda. So I'll go back to my coefficients and check where I have 3 here. If there are 2 of them, then there will be 2 additional terms here. That is it. That is it. If they are up to 10, I will have 10 of them there. Okay, because all of them are contributing to 3. All of them are contributing to 3. So you have that. Okay, let's rest a bit. Then we continue. Okay. Okay.
That thing you said about doing, I have a use one thing
All over again.
till 10 in the night.
You see, this is similar to what I was saying. Because you cannot, this lambda cannot disappear. Lambda is introduced on the right hand side. So lambda must be up here. My Oga come.
Damn it.
See now, this lambda must be up here.
The lambda must be.
Or you can continue.
Because it must be up here.
There's one particular equation in this. That means
This thing is
you
somehow
have
volatile.
soft test.
But we can get it from here. No, it's the same now. It can be different. It's just that this thing you use are different.
Yes. Now you must introduce a different alphabet up there,
Yes.
which is not on the left hand side. If you put
Otherwise
only
you
the
cannot
ones,
count
only
here.
other ones,
You
there will be
cannot
no,
count.
there will be
It
no,
treats- it treats.
yes. So
What's
even
the
if
one?
even if it's
Zika, I use Zika.
Yeah, it depends on what Zeta. No, it's the same. It depends on what you want to use and what you are used to. Like Prof doesn't use alpha beta. Here there isn't alpha beta. There is a nu here, right?
yeah, that is
And
it.
then it shows up here. You know, but it must be different from this alpha beta.
That is it. It must be different.
So you can't iterate it.
That is it.
The shortcuts now are introducing. Prof doesn't. Like you mentioned, you can just, once you have the gamma, you know, the suffixes on top, you can
Yes.
just, it doesn't add.
Yeah, that is it.
That is
This is not correct. It's not correct. It's not correct.
Do you have those books? Do you have it? I'm going to bring some for, I'll bring some for you guys to buy tomorrow. Prof, our class is reducing. People are running away.
I don't know if we can try
Try.
super body. Super body. Metric.
Okay, super good. Okay.
Maybe show me how I can do the translation.
That one is your first.
Yes. Maybe comparing compare.
No, that one we'll do it. We'll do it at individual level. That one is a bit advanced. If you bring that one there, people will run away. Okay, you said our class is reducing. Who again has gone?
Lady has gone.
You know, the lady said she wants to join mathematics.
Two guys.
Which, okay, this guy from.
They might come back tomorrow. I don't know.
Okay, they said they're going to where?
But they call them back to their schools.
Okay, to their.
Schools.
They didn't get permission.
But they said they told them to come back.
Oh, it's just a pretext to run away.
I don't know. This is what 15 applied. Only 10 showed up. Now they are moving.
We don't break it down like this. Even that.
This thing, like you said, it's actually it's still three. It's actually three.
Yes. Yes.
Follow the motion. Make you do everything. I did for rotational spherical. What do you call that? The rotational spherical. But not spherical. What you do with UVW, not article.
Yes. Yes.
Huh?
It's okay because he got 3 twice.
Yes.
Next
That's no, that's right. If you have a suffix up there to be 3, and then this other one is also 3, there is no need to, you can decide to do it separately, but you can couple them. There's a plus here now. See, the first one is gamma 2, 3. Can you see that? Can you see? No, gamma 2, 3. Then after the plus sign, you have gamma 3 what? 3, 3, 3 now.
For this second one. This is here. This is also here, but this is also
Oh, okay.
Okay,
Okay.
that's not an omission. Right?
Yes. Yes.
That's an omission.
No, it's correct.
2, okay, so it's an omission. Okay, yes, exactly.
There was no space, so I just put the square. Oh, welcome, sir.
What are they?
I'm fine, sir.
They're looking for space now.
Hmm. 5 minutes over. Huh? Let them come so that we continue. The lecture ends by what time? 12? It's okay. So,
I'm trying to understand what you're saying. This, you took the 2 together, the minus 3, 3, 3, and 3, 2, 3, isn't it?
yes.
This one is 3, 3, 3, right?
Yes.
So what is it looking for?
Now I will have written, you know there are 2 terms, but all of them are 3, 3. So I just put them together and squared.
No, I don't know. I'm trying to think. This is for minus sign and for cos that's together. So you have a 3 on top.
No, what he's saying is, look at the 5 dot squared there. That's what he's saying.
Okay.
It is done separately. That is two, 3, and 3, 3. Of course, 2, 3 will have the same equation. 3, 3 will have the same equation. Is it not necessary that the first one? Okay, but I was thinking that
The governing equation is what is on top, which is equal to 0, right? The governing equation.
Yes.
Then if you take since they are all 3, you don't need to do them separately.
Yeah, that is it.
And
That is
you
it.
do them one after the other. So you plug in the values there. The 5 dot dot is the first symbol there. Then 3 new lambda is 3, 2, 3,
That is it.
which is the down one here. Cot theta, right? Cot theta. You took the down one first, not the up one. Do you understand? Prof, is that what you did?
Yes.
This one is down one first.
Okay. Let's look at motion in the equatorial plane. We are still dealing with test particles. We are still dealing with test particles. Okay. And our aim here is to get the planetary equations of motion. Okay. Our aim here is to get the planetary equations of motion. That is our aim. Okay, we can get the planetary equations excuse me, of motion using the relativistic equation of motion that we saw previously, but it will be a bit more cumbersome. So we try to reduce the problem using the equatorial plane. Okay? You know what we mean by the equatorial plane? Okay, okay. Okay. So the equator is somewhere around here. Okay. So the equator is somewhere around there. So we want to try to see if we can study the motion of particles, of test particles, closer to the equatorial plane or on the equatorial plane, and derive our planetary equations of motion. Okay, as I said earlier, you can get it from the equation we just solved, but it will be a bit mathematically involved. So this one is a bit easier. Okay. So if we consider, let's say this is a star like a sun, and then we want to see a planet maybe at a point somewhere along the equatorial plane of that star. So our line element again is c squared d2 squared is equal to, so we are still in the Schwarzschild field. So our line element will be the same. 1 minus 2k over c squared r dt squared, okay, minus 1 minus 2k over c squared r to the power minus 1 dr squared minus r squared d theta squared minus r squared sine squared theta d phi squared. So that will be our line element. It remains the same. Okay. So the argument we are going to bring in is that at the equatorial plane, theta is pi over 2. At the equatorial plane, theta is pi over 2. Okay? If we are measuring angles from the z-axis, okay? So we are measuring our theta from the z-axis. Once you get to the equatorial plane, theta will be pi over 2. So if theta is pi over 2, then automatically the theta is 0. Are we together? Okay, because it's a constant. So this term will drop out. And what is sine pi over 2? Okay, so this will be 1. So our problem will reduce a bit. So we now have c squared d2 squared equal to c squared into 1 minus 2k on c squared r dt squared minus 1 minus 2k on c squared r to the power minus 1 dr squared minus r squared d phi squared. So our line element will reduce to that. Okay? So what if we now decide to divide all through by our proper time interval, d2? Okay? We divide all through by our proper time interval, d2. I'm going to end up with c squared equal to c squared into 1 minus 2k over c squared r. So here I'm going to have t dot squared. Okay? Minus 1 minus 2k on c squared r to the power minus 1 r dot squared minus r squared phi dot squared. So we have that. Okay? But from the motion of test particles, phi dot is L over r squared sine squared theta. Okay? And our t dot is 1 minus 2k over c squared r to the power minus 1. From what we did previously. Okay, we were able to solve the time equation and we got this. Okay, if we solve the Azimuthal equation, we also get this. Okay, so and we are at the equator. So this again will be 1. Okay, this again will be 1. So we'll end up with just L over r squared. We end up with just L over r squared. So if we substitute that into this equation, we substitute for t dot, and we substitute for phi dot. Okay? If we do that, we'll end up with an equation that has only r dot. Are we together? Okay. So if we carry out that substitution, we are going to end up with something like c squared equal to c squared into 1 minus 2k over c squared r. So our t dot squared will be this with a minus 2. Okay? So we have that 1, 2k over c squared r with that. Then you have minus 1 minus 2k over c squared r to the power minus 1 r dot squared. Then if we substitute phi dot squared, we are going to have minus r squared. So phi dot squared L will now become a squared, and r will take a power of 4. Is that not? R will take a power of 4. So this one will go. Are we together? Okay. So we have that. If I decide to multiply all through by this, okay, because my target is to get this. So if I multiply all through by this one will disappear. Okay, it's going to disappear. So if I multiply all through by that, I'm going to have c squared into 1 minus 2k or c squared r to be equal to, so this one will become squared. Is that not? And it will also go with this one. Are we together? Okay, so I'll end up with a c squared here. Minus, so this one goes r dot squared minus l squared over r squared into 1 minus 2k over c squared r. So I'll have something like that. So I can decide to make my r dot squared the subject of the formula. So I want to claim that my r dot squared will be of the form c squared. So I'm taking the r dot this way. So this one will come back this way. C squared into 1 minus 2k on c squared r. This term will remain minus l squared over r squared into 1 minus 2k over c squared r. So we have that. Any questions so far? So we have that. Okay. And you'll see that this c squared minus c squared will go once you open this bracket. Okay, it will go. And then this one will become, it will also cancel this other c squared. Okay. So you end up with just 2k over r. So you have just 2k over r, okay, minus l squared over r squared. Then I will have plus 2k l squared over c squared r cubed. Are we together? Okay. So if you were to solve this problem using the Newtonian theory, you end up with these two terms on the right hand side. We are using Newton's theory of gravitation to solve this problem. We end up with these two terms. So actually this term is a contribution of general relativity. Okay, this is a contribution of general relativity. And we are going to see how useful this contribution is. Okay, because we'll continue with this problem. We'll solve this problem and we'll get a conic section. Okay, once we get a conic section, you'll discover that a planet, if it's moving in an elliptical path, it will continue to move in that elliptical path. It cannot go out of that elliptical path. So this term brings in what we have as precision. We'll notice that our planets don't repeat the same orbit all the time. There's some sort of precision. Okay? If the sun is somewhere here, the planet moves like this for the first time. The second time when it's coming, there is a small angular difference with the first orbit. And that is contributed by this term. Okay? That is contributed by this term. And that actually, this is what gave general relativity the popularity it had. Because Newton's theory could not explain this precision, okay? But Einstein's theory was able to. So it gave it a lot of popularity. Are we together? Okay, so from there, we can decide to differentiate this again. Okay? Can decide to differentiate this again with respect to proper time. So we differentiate this again with respect to proper time. We are going to have 2r dot plus equal to, okay, once you differentiate this, you have minus 2k on r squared, r dot. Okay, this one will now give us a plus 2 L squared over R cubed, R dot. Then you have minus the 3 from here will contribute to these 2 and make it 6. Okay, you have 6 KL squared over C squared R to the power 4 R dot. So we have that. Are we together? Okay. So we can divide all through by R dot. We can divide all through by 2. If we do that, we'll end up with R dot dot being equal to what? Being equal to minus k over R squared, okay, plus L squared over R cubed minus 3k L squared over C squared R to the power 4. What is R dot? Which type of velocity? The instantaneous. Is it a velocity or a speed? Why is it not velocity? Why is it speed and not velocity? Okay. You are saying it's a velocity. Whether it is? No. It's not angular. Okay. What is our R? What is our R? What is R? Remember we started from Schwarzschild metric. And we define R as what? And remember we're working with okay, R is just the radial distance. Okay? No, not Schwarzschild radius. That's a different thing entirely. R is just the radial distance. Okay? So R dot will be the instantaneous radial speed. It's not a velocity because we are not bringing in the vector components. Okay? So it's just a speed. Okay, and then this is also the instantaneous acceleration. And then again, we have a contribution from general relativity. Okay, this last term is a contribution from general relativity, which is not there in Newtonian. Okay. So actually, if you look at this, this is our planetary equation of motion. But it's not in a palatable form. We need to cook it. Okay? It's just like raw yam. We need to fine-tune it and cook it with some oil and spices so that it can look better in our eyes. Okay, like this, you cannot appreciate most of the things happening there. So we need to fine-tune it, let it look better. Let it look better. So how do we go about that? How do we go about that? Okay, we're going to introduce a new parameter, u, which is a function of our azimuthal angle phi. Okay, that's what we are going to do. So we introduce a u, which is a function of phi, and we define that u as just 1 over r. Okay, we define that u as 1 over r, and they are all functions of phi. That's what we are going to do. So if u is that, then r is what? 1 over u. Okay? R is just that. So what will be r dot? What is r dot? R dot is the r by the 2. Okay? But remember, we have said r is now a function of phi. So this will now be the r, the phi, the 2. Okay? And we know that the phi, the 2 is phi dot. Is that not? It's phi dot. So we end up with phi dot, the r, the phi. Okay? Which I can still write this as phi dot, the r, the u, the phi. Okay? Which is the same as phi dot. What is the r du? The r du will minus 1 over u squared. Okay? So I have minus 1 on u squared. Okay? And I have du by the phi. Okay, so I'll have that. Remember, we had defined our phi dot in the equatorial plane to be L over, you said it's L over what? Over r squared sine squared theta. Is that not? But since we are working in the equatorial plane, the sine squared theta reduces to 1. So I will now have this as L over r squared minus u squared du by the phi. I have that. But 1 over r squared is 1 over r is u. 1 over r is u. So 1 over r squared will be u squared, is that not? So that u squared will cancel this other u squared. So I'll end up with just minus L du by d phi to be my r dot. Are we together? Are we together? Okay. We have gotten r dot, but our equation is in r dot dot. So we need to extend to r dot dot so that we can substitute into this equation. So how do we go about that? So we take a second differential. Let's take a second differential. Okay. So my r dot dot will be the r dot d2. Is that not? Okay. Which will be d d2 of r dot. Or let me just put it this way. It will just be the r dot d phi by d2. And put it that way. And I will now have phi dot d phi of r dot, okay, which is the same as phi dot d phi of r dot. What is our r dot? Minus L du by d phi. So minus L du by d phi. So I'll have that. Okay, so from there, remember L is a constant. Actually, L is the orbital angular momentum. Okay, L is the orbital angular momentum. So from there, I can have, remember my phi dot is minus L over r squared. Whether it's L over r squared. The minus is from here. Okay. So the other L will come out. So you have L squared. Are we together? Then I will now have, instead of having r squared here, I will have u squared. Because r is 1 over u. Then I will have d squared u d phi squared. So that will be my r dot dot. So I can now substitute it into my equation. So in place of r dot, I'm going to put minus L squared u squared d squared u by d phi squared. Okay. And then should be equal to minus k. In place of, I'll put u squared. Okay. So I'll plus L squared u cube minus 3k L squared over c squared u to the power 4. So I'll have that. Okay? You discover that u squared is common. Okay? So I can divide all through by minus L squared u squared. So if I divide all through by that, I will have the squared u, the phi squared equal to, so this will become plus, is that not? This will become plus L over K over L squared. This one will now become minus. The L squared will cancel, that will cancel. So I'll end up with what? I'll end up with u. Is that not? This one will become plus. The 3 will remain. The K will remain. The L is going. And the u will become squared. And then the C squared remains. So I'll have that. Okay. So I'll have that. So I can rewrite that. I can rewrite it as the squared u, the phi squared, plus u equal to k over L squared plus 3k over c squared u squared. And actually this is Einstein's planetary equation of motion. Okay. Planetary equation of motion. And again, we have this contribution that is not there in Newtonian. We have this contribution. So we need to attempt a solution to that equation. We need to attempt a solution to it. And remember, it's a second order differential equation. Okay, so we are going to have a complementary solution and a particular solution. Okay? But to solve this equation, it's a bit more complicated. So we'll isolate the Newtonian part and solve it. Then we'll use the solution of the Newtonian part as a particular solution of the Einstein part. Did you get what I said? To solve this directly is a bit difficult. So we will forget about the Einstein term, okay, and solve this one and get u. Once we get the u here, they will now use that u as a particular solution to Einstein's solution. Some sort of successive approximation. Okay? Some sort of successive approximation. It's like some sort of iteration, first iteration. You get the first approximate substitute, get the better approximate substitute, and so on. So it's something like that. Okay? So let's see if we can appreciate that. So if we are isolating the Newtonian, then we have d squared u, d phi squared plus u equal to k over L squared. So we are leaving out the Einstein term. Leaving out the Einstein term. So what is the complementary solution? This one is, if you look at this side, because this is the complementary part of the equation. If you look at this side, you discover any sine or any cosine. You differentiate it 2 times, you have a minus of it, plus something, it will give you 0. Is that not? Any sine or any cosine. You differentiate it twice, it will give you its minus, which when you add to this, it will give you 0. Because the complementary solution is when the right-hand side is 0. When the right-hand side is 0, we get a complementary solution. And then the particular solution is the solution of the right-hand side. And the solution of the right-hand side here is just simply this. Because this is not a function of u. So the particular solution will just be this. While the complementary solution will be either a sine or a cosine function. Okay, so what is our complementary solution? Our u complementary. Our u complementary will be either a certain a cos phi plus alpha, can use that, or a certain b sine phi plus alpha. Can I use any of them? It will serve as my complementary solution. And my particular solution will just be what I have on the right hand side. So if I decide to use the cosine, then my complete solution will be, remember, we are putting phi here because our u was defined in terms of phi. Okay? We defined our u as a function of phi. So that's why we have to use phi here. So I have a cos phi plus alpha plus the particular solution, which is k over L squared. And actually this my k is small k. This my k is small k. Which k is this? This k is what's the difference between this k and this one? This k is this is capital K. This one is and then what of this one? Okay. Okay, what of this? This is capital K. This one is, and this one is big K. Okay, so this one is capital K, this one is small k, this one is big K. Oh. You know, there are some people who call capital letters big A. I can also claim that this is big A. Okay, and then this is small a. Okay, so this one is small a, this one is big A. Okay. All right, so our u is of that form. Our u is of that form. So remember, we started with R. We started with R as 1 over U. So we want to have our R now as a function of phi. Our R will be 1 over U, which is 1 over K over L squared plus A cos phi plus alpha. That is my R. So I can decide to factorize out this K over L squared. So if I do that, my R will be, so if I factorize K over L squared, it can go up and become L squared over K. Okay? Then I now have 1 plus epsilon cos plus alpha, where I will define my epsilon as what? Epsilon is K L squared over what is A L squared over K. Okay? Because we are factorizing it out. So we have that. So my epsilon will be that. Okay? Actually, this is the Newtonian solution to the planetary equation of motion. Okay? It's the Newtonian solution to the planetary equation of motion. And actually, it's a polar equation of a conic section. Okay? It's the polar equation of a conic section, where epsilon is our eccentricity. Okay? Remember, if epsilon is 0, we have what? A circle. If epsilon is 1, we have a parabola. If epsilon is greater than 1, we have what? A hyperbola. And if epsilon is less than 1, we have an ellipse. So that's the equation of a conic section, which is actually Newton's solution to the planetary equation of motion. And epsilon is 0. It's a circle. No? You have forgotten your mathematical methods. Okay? If epsilon is 0, we have a circle. If epsilon is 1, epsilon is equal to 0, we have a circle. Epsilon is equal to 1, we have a, if it's equal to 1, we have what? A parabola. If it is less than 1, we have an ellipse. If it is greater than 1, we have a hyperbola. Okay? We have a hyperbola. Okay? So, after getting this, we now need to push it further to get a solution to Einstein's planetary equation. Okay? So let's push it further. So as I said earlier, according to this equation, a planet will trace the same path throughout. The path will not change. Okay? If it is an elliptical path, it will continue in that elliptical path without any change. Because there's nothing in this equation that can cause a change. Okay? It will continue moving in that path without any change. But what is observed astronomically it's not that. There is a precision. Although the angle is very small. Okay? It's in minute seconds. Minute seconds. Okay, at times when you calculate it, it's minute seconds per century. Okay? Minute seconds per century. So it will continue moving. So you have just a small, there's just a small precision. Very small precision.
It doesn't because of the fact that our galaxy is moving. That's why
Okay, what is causing the precision? Okay, what is causing the precision? So it could be because of that. There are many reasons that could cause the precision. In the first place, remember when we started solving this problem, we said our mass was spherically symmetric. Okay? But is our mass spherically symmetric? It's not. Okay, so we have is some sort of an oblique spheroid. Okay, it bulges at the equator and flattens at the poles. Okay, so it's some sort of an oblique spheroid. Okay. Oblique spheroid. Okay, so we are looking at spherically symmetric. From spherically symmetric, you can extend it to this. Okay, from spherically symmetric, you can now move out of spherical symmetry to oblique spheroid. But if you are not familiar with spherically symmetric, it will be very difficult to extend from there to this. Okay? That's what I want to convince this my Oga to do. Okay, to move out of this to this. That's what I want to convince him to do. Okay? And it's a very interesting adventure. Very, very interesting one. Okay? So we'll take the solution of the pure Newtonian, as I said, and insert it on the right-hand side of this equation. So instead of having our u here, we'll substitute that one there. We're going to substitute this solution on the right-hand side of this equation. Okay? So we are going to substitute that. And once you substitute that, your equation will be of the form d squared u d phi squared plus u minus k over L squared equal to 3k over c squared. Okay, so I will now substitute this other one. I will now substitute that. So we have L squared over k all over 1 plus epsilon cos phi plus alpha, all of that squared. So we'll have something like that. Okay? That is? Okay. So once we take the inverse of that, we are taking it because this is R. So we are using U. So we are using U. We are going to have K over L squared, okay, into 1 plus epsilon cos phi plus alpha. So I'm going to have that. Okay. So we're going to have that. And the solution of this equation is of the form u of phi is the same as k over L squared into 1 plus epsilon cos phi minus alpha minus 3k squared over c squared L squared phi is of this form. Okay, you can read about this. How we deduce this from this is simple. Okay, and if you look at this solution and you look at this other one, you will see there is a term here that is being subtracted from phi. Okay, so when the planet goes round once, when it's coming back, it will not follow the same path. The path will deviate. The path will deviate a bit. Okay, there's going to be some sort of precision. Some sort of precision. Okay, so we can continue from this to deduce the precision. To deduce the expression for the precision. Okay, but that one I will allow you to look at it yourself. How do you get the precision from this? Okay, how do you get the precision from this? So the only phenomenon we are left with that we have not looked at is deflection of light. Okay, it's deflection of light. It's deflection of light. So tomorrow, briefly before our afternoon lecture, I'll take the first 30 minutes of that lecture to rush through deflection of light. Then we will now go into our research questions. Okay? So this is a convenient point to stop.